Cool. All right, so starting off with valence, good news. That was all reviews. So starting off today, we're going to talk about valence electrons. And right, the reason why carbon likes to have 4 bonds is because it already has 4 valence electrons. And so in order to complete its octet, it needs to create 4 bonds so that it has 8 electrons in its octet. Okay, and actually the number of valence electrons that an element has kind of neatly corresponds to where it lives on the periodic table. So if we were looking at just a blank periodic table here, you just start numbering your columns from left to right. So everything in this first column here has 1 valence electron. Everything in the next column has 2 valence electrons. And then you actually skip over those transition metals. I mean, first of all, they're not going to be involved in this course really whatsoever. We don't talk about metals very much in organic chemistry, but also their valence shell is a little bit messed up because they have these 3D electrons or 4D. Anyway, skip over. So the borons and the aluminums of the world have 3 valence electrons. Carbon has 4 valence electrons, nitrogen 5, oxygen 6, fluorine 7, and the noble gases have 8. All right, and actually helium's kind of an exception because it's teeny tiny, it only has 2. But we put it in the noble gas category because it behaves a lot like a noble gas. Do you remember why the noble, how the noble gases got their name? The one property that they share? Right, basically they are unreactive. You cannot form a bond with helium to save your life. Okay, they already have a complete valence shell, which means they don't want to engage in any sort of bonding. They don't want to share electrons. They don't want to give them up. They don't want to accept them. None of that business. They're already happy as they are. They just want to be left alone. Every other element forms bonds in order to complete its octet. Okay, so the whole reason why elements are forming bonds is so that they can share electrons and get to that 8, that magic number, that complete octet, which then allows them to be, more stable. So because of that, because it's sort of as simple as everything within a given group or a given column shares the same number of valence electrons, that means that if we had this rule that carbon likes to have 4 bonds, we can say the same thing about everything in that category there. So silicon also like to have 4 bonds. And actually, I am lying a little bit. It's specifically the non-metals on the periodic table. So everything above that little zigzaggy line. But nonetheless, so nitrogen likes to have 3 bonds. And 1 lone pair. We could say the same thing about phosphorus because phosphorus lives right underneath nitrogen. These elements do not play as important of a role in organic chemistry, but nonetheless, in terms of just being able to draw these Lewis structures and sticking to these simple rules, everything within this same category, within this same within this same column has the same sort of bonding properties. They want the same number of bonds and the same number of lone pairs. Okay. All right. Oops. Cool. All right. So again, this chapter is going to be all about structures. Now we're going to just kind of expand upon our knowledge of structures or use of these structures and talk about formal charges. Okay. The most stable structures do not have any formal charges associated with them. Nonetheless, sometimes those higher energy species, some molecules that have formal charges are going to be important in chemical reactions. All right, so we're going to see often when we start doing reaction mechanisms and all that good stuff, that we'll see structures that have formal charges. So we just need to be able to write them, represent them, kind of understand when a structure has one. Okay. So strictly speaking, Let's actually just draw an example here. What's going to be a simple one? All right, so here's a structural formula for water. And then we have here is a hydronium ion, okay, or H3O plus. This will be an important molecule when we start talking about acids and bases. Okay, and again, just to reiterate, our goal right here is just to sort of understand and be able to see these formal charges. We're going to see that this structure right here has a formal charge of +1, and this one has a formal charge of 0, right? So given a Lewis structure, we want to be able to see whether or not there is a formal charge. And we're going to have a long way and then an easy way to do this, kind of similar to what we were talking about with our Lewis structures. Okay, so formal charge is equal to the number of valence electrons an atom has, and specifically the number of valence electrons an atom has when it's all by itself, minus the number of electrons in our Lewis structure. All right, so this one here, number of valence electrons an atom has, we just get that from the periodic table. This is like if I had, for example, in this case, an oxygen atom all by itself, how many valence electrons is it bringing to the table? Which part? So yeah, so formal charge is equal to the number of valence electrons that an atom has when it's all by itself, minus the number of electrons that it has in the Lewis structure that you're looking at. Okay, and we'll talk about how we get this second part in 1 second. Let's make sure that we understand that we can figure out how many valence electrons an atom has when it's all by itself. Okay, so in particular, I'm going to be looking at the oxygen in each of these Lewis structures. Okay, and we're going to calculate formal charge for each of them. So let me move my little cheat sheet formula down here. Formal charge is going to be equal to the number of valence electrons that oxygen has when it's all by itself. So going back to our periodic table, that's not what I wanted to do. How many valence electrons does oxygen have when it's all by itself? This is what I get from my periodic table based on what column oxygen lives in. So how many would it be? Everybody put it in the chat. All right, so we just start counting. I mean, I left my labels on here, so hopefully it's pretty obvious, but because oxygen lives in this particular column, it has 6 valence electrons to start with. So in both of my formal charge calculations, whoops, I'm going to start with the 6. And then we have to subtract the number of electrons that this oxygen has in my Lewis structure here. And what I mean by that is we're going to go through, we're going to count all lone pair electrons. So this is 1, 2, 3, 4, and then half of each covalent bond. So you're only going to count 1 electron from each of these 2 covalent bonds. So in this particular structure here for water, I have 6 electrons associated with that oxygen in this structure, giving me a formal charge of 0. Okay. Again, you're going to count 1 electron from each covalent bond. So it's not the same sort of calculation that you're doing when you're making sure oxygen has a full octet, where you're counting each covalent bond as 2. You're only counting half of each covalent bond. If we move over here to this structure, oops. Again, the number of valence electrons that oxygen has when it's all by itself, that number doesn't change. But take a second and see if you can't count how many are associated with that oxygen in this Lewis structure here. We're going to count both of them from the lone pair, 1, 2. and then 3, 4, 5. So this means this structure has a formal charge of +4. What's up? Somebody have a question? No, we're good? Okay. All right, so these are two different molecules. They're very similar to one another, right? There's just an additional hydrogen oxygen bond. This one has a formal charge of +1, whereas this one has a formal charge of 0. Okay, so let's do another one here. I want you guys to try this one on your own. All right, see if you can't give me the formal charge on the nitrogen in these two species here. All right, so first of all, based on nitrogen's position on the periodic table, how many electrons does it have in its valence shell when it's all by itself? Show me on the screen. Cool, right? So we got 5 valence electrons for nitrogen when it's all by itself. If we're gonna look in each of our structures here, we have 1, 2, 3, 4, 5 for the ammonia. So this is an example where the formal charge is equal to 0. All right, and then in this other structure, we have, again, I'm going to sort of put this box around the atom that I'm talking about, and I'm going to count all the electrons in that box. 1, 2, 3, 4, 5, 6. So 5 minus 6 equals -1. Now, again, there's an even easier way to do this. And again, this is just the benefit of being in organic chemistry and the fact that we're talking about so few elements. We can just have a way simpler set of rules than look on the periodic table, count in the box, blah, 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 blah. If you notice at the beginning, we said that oxygen likes to have 2 bonds and 2 lone pairs, right? When we do that, we see that we have a formal charge of 0. It's when we go outside of those rules that we end up having a formal charge, a net formal charge. So in my hydronium ion, I actually had 3 bonds and only 1 lone pair, right? So I sort of broke that simple rule for drawing Lewis structures. So same thing with my nitrogen. I says nitrogen likes to have 3 bonds and 1 lone pair. That would give it a formal charge of 0. Those are the most stable structures for nitrogen for sure. But if you see a nitrogen that has 2 bonds and 2 lone pairs, that means it has a formal charge. Okay, so we can sort of, just like we did before, we can narrow it down to this simpler set of rules. Oops, let's do this. Where we say, okay, if we have an oxygen that has 2 bonds Okay, when we have an oxygen that has 2 bonds and 2 lone pairs, that will give us a formal charge of 0. What we saw is that when that oxygen has 3 bonds and 1 lone pair, that will give us a formal charge of +1. And on the flip side, we could see it with just 1 bond and 3 lone pairs. And that will give it a formal charge of -1. All right, so we had this simple set of rules for drawing the Lewis structures. Those will give you the most stable Lewis structures for sure. But again, oftentimes chemical reactions are driven by oftentimes just the temporary formation of these less stable species. And we want to be able to recognize those as well. And again, we can do so again just by simply looking at the bonding pattern. How many bonds, how many lone pairs? That will tell us our formal charge. Okay. Importantly, you'll notice that if you summed up the number of bonds and the number of lone pairs, you will always still have 8 electrons in the valence shell, right? You'll never see oxygen with just 6 electrons in its valence shell or something like that. So if you see somebody getting lazy and just drawing something like this, you can already tell that this oxygen atom right here needs to have 3 electrons and thus a negative formal charge, whereas this oxygen will have 2 lone pair electrons, and I think I missed the word lone pair, 2 lone pairs electrons and a formal charge of 0. Actually, the kind of convention, if they leave off the charge, they're really doing it wrong. But oftentimes you will see the lone pairs left off. We get kind of like, oh, we don't know these. Sorry. We don't know bond line structures yet. My bad. Carbon. Something like this. We know automatically that this oxygen has a negative charge because there's only 1 bond associated with it and 3 lone pairs. Okay, and again, if they left off the charge, they're kind of doing it wrong, but you will see this type of thing often. It is not uncommon. You know, what you're going to see is as we get better and better with these structures, we also get lazier and lazier and kind of leave stuff to be implied. Right, so oftentimes you won't see lone pairs explicitly written. You kind of just have to know that they're there because oxygen always has this full octet. So we can do the same thing with nitrogen, where we're again going to make a little cheat sheet of simple rules here, number of bonds. Formal charge. Again, we said that when nitrogen has 3 bonds and 1 lone pair, that's the most stable form of nitrogen. That's when it has a formal charge of 0. But when it has just 2 bonds and 2 lone pairs, it will have a formal charge of -1. All right, everybody take a second and see if you can't fill in what should be this last category for me here, following just these sort of patterns that you see. When are you going to have a nitrogen that has a formal charge of +1? Okay, so this will occur when you have a nitrogen that has 4 bonds and 0 lone pairs. Now, this table of numbers might make your head hurt a little bit, but let's just see that there's actually kind of a fairly simple pattern. If we look at the number of bonds for oxygen, right, when it has those 2 bonds, the formal charge is 0. Less than that, it will have a negative formal charge. More than that, it will have a positive formal charge. Same thing down here. If we look at the number of bonds for nitrogen, we know it likes to have 3. If it has anything less than that, it's going to have a negative formal charge. If it has anything more than that, it's going to have a positive formal charge. Okay, so we don't really have to like memorize the whole table or anything like that. It's just kind of as simple as spotting the number of bonds. And then you can deduce from that number of lone pairs and formal charge. Because again, just like oxygen, we saw that nitrogen has to have 8 electrons in its valence shell. All right, so it's like if you know the one piece of information, you can always figure out the other one.
So it couldn't be like 1 lone pair and then like 2 bonds then?
No,
Would that make
no,
sense?
because
Okay.
that's going to violate the octet rule. And we will see like carbon can kind of violate the octet rule every once in a while. Oxygen and nitrogen will absolutely never violate that octet rule. They're just too electronegative. It just doesn't happen. So we can always kind of stick to these simple set of rules rather than going through the calculation every single time. Okay, so we're going to do a lot of looking at structures and trying to just be able to spot that in our practice today. We got one more thing that we're going to learn that's brand new. And this is kind of, I kind of accidentally teased it, but this idea of bond line structures. Right, so we had this structural formula, which is again just a fancy way of saying a Lewis structure. Right, so this would be for this carbon, this 3 carbon compound. We actually call this propane. Again, we don't know how to name things yet. We'll get to that. But this is C3H8. Okay. Now, like I was saying, a lot of organic chemistry, a lot of the skills that we're going to learn, are motivated by laziness. Those bond line structure or those structural formulas take a long time to draw. You got to go through and draw each individual hydrogen, da, 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 da. So we have this equivalent way of drawing structures called bond line structures, where this would be the same thing. All right, just this zigzaggy line right here represents this same molecule propane. A lot of times when you see like images of organic chemistry, you see a lot of hexagons going on, right? Who here has seen a hexagon associated with organic chemistry? Okay, this is a bond line structure and it contains the same information as our structural formula, just with less writing. Okay, so we're going to go through and sort of learn how to interpret these bond line structures. Okay, and again, they're great because they take way less time to draw. They're way less busy. They're actually easier to interpret for big structures because they're just less busy. There's less going on there. Okay, so each endpoint and intersection of my bond line structure represents a carbon atom. So this endpoint right here corresponds to this carbon atom. This intersection of these 2 lines right here represents this middle carbon. And this endpoint right here represents that last carbon. okay? So the position of those carbon atoms is implied in this bond line structure. All right, but we'll talk about the hydrogens here in a second, but everybody take a minute and tell me how many carbon atoms I have in each of these two bond line structures that I just drew. Okay, so this one, again, every endpoint and intersection. So this is 1, 2, 3, 4, 5 carbons. So C5. And this one would be 1, 2, 3, 4, 5, 6, right? So those hexagons represent 6 carbon rings. So again, that's our structural formula. This is what we call a bond line structure. Okay, so the position, I counted 1 twice. So the position of these carbon atoms are implied in this structure here based on being, again, they're either the endpoints or the intersections. The hydrogen atoms are also implied in these structures, okay? And how we figure that out is we just know our rule for completing carbon's octet. Okay, so basically you go through, you count carbons, and then you're just going to make sure to decorate them with however many hydrogens that they need in order to complete their octet. So if we go in here to this one, this green carbon atom here, as it's drawn, it has one bond already explicitly drawn, that green carbon to orange carbon bond, which means that I would need to decorate it with 3 hydrogens in order to complete its octet. Same thing with my pink one on the other end here. It has one bond already explicitly drawn, that carbon-carbon bond, which means it has 3 hydrogens that are implicitly drawn, or that need to be implicitly drawn. Looking at that orange carbon atom, everybody take a second, put it in the chat. How many hydrogen atoms do you think I need to add to this middle orange carbon? Awesome. All right. Yeah, so this already has 2 bonds explicitly drawn. So I would just go in there and fill it in with these 2 bonds. Okay, so again, these are equivalent pieces of information. They tell you the exact same thing. One's just like a shorthand. It's a quick way of doing it. And it takes a little bit more work, but once you get good at reading them, it's like a time saver, right? Again, the position of those carbons are implied because they're at the endpoints and the intersections of those lines. And the hydrogens are implied because you're just going to go in and fill them in where they need to be in order to complete carbon's octet. Okay, any other element that's in these structures would not be implied. So for example, if I was going to draw what we're going to learn is called a alcohol, whoops, all right, if I were going to do the bond line structure for that, the oxygen is going to be explicitly drawn. Any other atom other than carbon and hydrogen is going to be explicitly drawn. And if that oxygen is bound to a hydrogen, notice that that's also explicitly drawn. Okay, so the only thing implicit from this structure here is that it has 1, 2, 3 carbons, and then I would fill in the hydrogens on those carbons. Okay, every other atom again would be explicitly represented. If there was a nitrogen in there, there'd be an N in there, et cetera, et cetera. Okay, so everybody take a second and see if you can't complete the molecular formula for this one here. How many hydrogens should I have in this 5-carbon structure that I've drawn? Yeah, good job, Anna. Yeah, looks good. Yeah, so seem to be getting the hang. And this is just something that comes with sort of practice, but you just get really good at looking at these and realizing, all right, if it's at the end here, that means I'm going to need 3. If it's a connection of 2 lines, that means I'm going to need to put in 2. And again, we got another endpoint here. So this would be 3. Okay, so to finish off this formula, this would be C5H12. This is what we call pentane written here. If we go over to our ring, all these carbons already have 2 bonds, right? So that means that I can, that each one just needs to have 2 hydrogens. All right, so we learned about our structural formulas, or what we called Lewis structures. Now we have a different molecular representation, these bond line structures. And again, the benefit of the bond line structure is that they're just quicker to draw. Okay, so let's do a few more practices with bond line structures, and then we're going to incorporate this formal charge business into that as well. That's what we'll do for the last little bit here. So for this one, you're going to give me the molecular formula. For this one, I want you to fill in formal charge and lone pairs. All right, and then we're going to tie it all together with these two, where you're going to do the same thing. All right, and everybody actually take a second and type your name for me in this, the name as it appears on my roster into the chat. I'm just going to download the chat at the end, and that's how I'm going to take attendance. So everybody just type the name, your full name in as it appears on my roster into the chat, and that's how we'll do this. I'm gonna go through and start putting in answers, and then we'll discuss. We're gonna run out of time here, so I just want to go through this quick. All right, so to just go through quick. So again, for my bond line structure, I just need to go in and put in all the implied hydrogen. Well, I guess first of all, let's count carbons. 1, 2, 3, 4, 5. Then I'm going to go through and put in my implied hydrogens by making sure that carbon always has 4 bonds. So 3 on the end. Well, that was pretty wonky. 2 here. This carbon is going to be the one that we haven't seen before. It already has 3 bonds, so you would only need to put 1 hydrogen on there. And then each of these ones that are sticking out on the end need 3. All right, formal charge. We could do it the long way where we're thinking about the formula. But again, the easiest thing to do is just ask yourself, how many bonds does nitrogen like to have? 3. In this structure, it has more than that, right? Plus 1 bond means that it has a formal charge of plus 1. Same thing in my next structure with my oxygen. Oxygen likes to have 2 bonds. In this structure down here, it has 3. So an extra bond gives it a formal charge of plus 1. I also asked for lone pairs, so we need to make sure to always complete everybody's octet. So if oxygen has 3 bonds, that means that it needs 2 electrons or 1 lone pair. Okay, and then tying it all together with our, mixing of formal charges and bond line structures here. So first of all, this molecule has 1, 2, 3 carbons. The implied hydrogens are only going to be on those implied carbons. So 1, 2, 3, 4, 5, 6, 7. So C3, H7, O. That would be my molecular formula. And then here, oxygen likes to have 2 bonds. In this particular structure, it only has 1, so it has 1 fewer, meaning that it has a formal charge of -1. And again, making sure to put in all those lone pairs, it would have 3. Right, so 1 extra bond means a formal charge of +1. 1 fewer bonds means a formal charge of -1. And you can just check that out with this little table that we built, that all checks out. All right, so again, we're just going to start with those simple rules that we learned about how many bonds a particular element likes. So then see if you can't do this last one here in this remaining 0 seconds that we have. So I guess never mind. Let me just do it real quick. 1, 2, 3, 4 carbons. C4.
Recording.
3, 6, 9. So H9. And then we have our NH at the end. This nitrogen has 2 bonds, which is 1 fewer than it likes to have. So that means it has a formal charge of -1. In order to complete the octet, I would need to put in 2 lone pairs of electrons.
So when it's NH, that means it's a bond, right? When it's
Yeah, that means
like
that there's a bond with the nitrogen. I could have drawn it more explicitly,
like another
right,
like
by
line
doing
or whatever,
something
right?
like this. But
Okay.
again, it's all about being lazy and condensing things down, right? So you
Okay.
will often
Yeah.
see it as OH or NH rather than the bond explicitly drawn.
Okay. All right. That makes sense.
Cool. All right. So, it's a little weird because at this point, we don't really know why we're using these structures yet or anything like that. It's more or less like we're building up our tool chest, right? So that when we move on to this next chapter, we can talk about organic chemistry. Right now, we're just building skills with drawing those molecules. We haven't even really learned anything about these molecules yet. So y'all just bear with me that you got these skills, that we need to know how to draw these things, interpret whether there's a charge, interpret where those lone pairs are, et cetera, et cetera.